Alright, I think this is working. So I was given some AP Classroom questions to do. This question, it's asking about conservation of energy for like a rolling object down a ramp. Um, it's pretty much conceptual. You can't really solve for much mathematically. It's asking about the energy at the bottom of a ramp in terms of the initial energy, and it's of the sphere ramp Earth system, so it's going to be conserved in most instances because of Newton's third law, which is each action has an equal and opposite reaction in terms of forces. So like the force of friction acting on the ball will also act on the ramp, which acts on the Earth. So it's conserved, but the thing to notice is that for like if there's obviously if mu, the coefficient of friction, is 0, then there's no friction, so there's energy is going to be conserved. If it's big, then the ball is going to roll. It's going to roll perfectly, but that also, like any energy lost by the ball in terms of potential energy will be gained as kinetic energy at the bottom, so it's still conserved. But if the mu is low, the ball will roll and slip, and we don't really have a way of mathematically calculating it unless you know how it slips. So energy will actually be lost because of the friction, as it'll be heat energy, which is not a type of mechanical energy. So for small mu values, I think it'll actually dip down, so this is the correct answer. Um, if we were assuming no energy was dissipated as heat, which it doesn't say, this would be the correct answer. But kind of a weird question. You could probably show that it's the same for like the begin for mu is 0 and then mu is like very high if you had real values, but we don't. So yeah, that's the correct answer, I believe. For 35, this is a Newton shell theorem question, which basically says that if an object, let's say a point mass, was inside of a uniformly dense spherical mass, like a planet, then um, the force of gravity essentially would only account for, like, if suppose this is the center mass of the planet and then there's like a point mass P here. If we drew a shell radius around the center mass with the radius being the distance between the two, only the mass, the physical mass of the planet within that shell would cause gravity, cause a force of gravity. All the other mass would cancel out. Like you could think of in terms of reasoning wise, as gravity is inversely proportional um, to the square of distance. So like all this mass here is very close to the point, but it's very little mass in terms of that triangle. So it would have like a pole that's equal to all of the mass at this triangle, because this triangle is going to be all the stuff is farther away, so the gravity would have a smaller pole, but it's more mass. So they cancel out, but everything inside of the sphere will still have mass. So the formula we use, Fg is equal to G, and then M object, as always, times the mass enclosed. We call that M prime. Usually that's the difference between what we normally do is just the mass of the planet, and then the radius enclosed squared. Um, let's see what it's asking for. Uh, D, okay, in terms of D. So on the bottom, we're going to have G, or sorry, for Fg, it's equal to G. Ms is, I believe, the mass of the stone. Yeah, okay. Ms, and our radius is going to be D squared. Now we have to find the mass of the planet. So mass of planet equals density, which is rho, times volume. Alright. So we can basically, what we can do is this. We can find rho, and then we can apply that rho to a smaller volume, which is the enclosed volume. That's sphere here is the enclosed volume, so you can use it because it's going to have the same density as the entire sphere, so you can use that to find the mass enclosed. So rho equals mp over, we have the volume of the sphere is 4/3 pi, and then rp is radius of the planet cubed. So rho. And now if we want to find the mass enclosed, we multiply this by the volume enclosed. So all of that times 4/3 pi d cubed. Okay, so we have to put all of this up here. So it's going to be equal to g. These 4/3 cancel out. G ms mp times d cubed over rp cubed all over d squared. So those cancel out, and we get g ms mp times d over rp cubed. What does this show us? This shows us that while d is between 0 and rp, it shows us that the force of gravity is directly proportional to the distance from the center, because rp stays the same as the radius of the planet. So this should probably be the correct answer. And you can do unit matching here. It makes sense. The unit is whatever g is times kg squared mass times, or it's over times distance over distance cubed. So it's the same unit as the regular formula, so it should be correct. I'll just do some other practice exam questions that are probably useful. This one's asking for the speed. Okay, so it starts at rest. That's the important thing, and we're given acceleration. So speed it's the absolute value of velocity, but velocity is it's the antiderivative of acceleration. So we're given t squared over 90 meters per second. Now we take the integral dt from 0 to 30 seconds. If there was an initial speed, we would have to add that on. That would be like some sort of constant. Like if it said we started at 4 meters per second, we would add that on outside the integral. But otherwise, this is just 30 cubed over 3 times 90, 270. So I don't feel like doing that, but times 10 cubed over okay, so that's 100. Alright, this is a valuable one because a lot of people still don't understand how lever arms work. Essentially, the lever arm is like if you were to draw a radius between a force and the axis of rotation. That's what your lever arm is. So like here, this is the axis of rotation, the blue. The red is your origin of the force, and then between them you have your lever arm. Right, and the angle you input, the formula for torque is equal, it's a cross product, is equal to RF, I believe it's sine theta. So in this case, theta is the angle between the force and the radius. So like you'll see the radius is, if you were to draw an arrow, it's going out this way. Hi Brian. And the force is being acted in this direction. So if you were to move this vector here and put it over here, the angle between them is what goes into the sine. Alright, so to actually do the question, it's asking for the torque. I believe the angle between the torque and the radius is actually 63. So it's a sine of 63 degrees. So I believe that is 4/5 times the radius is 0.5 meters times the force is 100 newtons. So that's a 50 over 5, 25 times 4. It's 100, I guess. If I didn't know, I didn't do that right. I can't do math. 40. Okay, yeah, that checks out, I think. I hope. Yeah, 40. All right. Next question. And the reason you want to think of like this conceptually, if you push a door from the edge of the door inwards towards the hinge, you're gonna do no torque whatsoever. You won't be able to move the door like if you're pushing on the edge of the door. Whereas if you push perpendicularly, you'll have the easiest time. If you push, if this was a bird's eye view of a door, the hinge is here. The radius would be out this way, so if the force is inwards this way, your lever arm is going to have an angle of 180 degrees, and the sine of 180 is, well, it's 0, so you would do no torque. What is the speed of the other fragment? When the brick is falling at a distance d, it explodes. Okay, cool. So this is conservation of momentum. So brick, let's say the mass of the brick is m. Alright, so it says one fragment is instantaneously at rest. So our initial momentum is m times 0. This question is only in terms of the xy plane, not the z-axis, which is like the vertical. So you can ignore the drop. That's just saying, like, that's just setting up the question. So 0 is the initial, I believe. Yeah, one's at rest, so the only other explanation would be that the other's at rest, that I can think of. Because, well, it's not, you could also do conservation of energy. Oh, actually, maybe this is, it doesn't say it hits something and explodes. Okay. So what this, so there is work done. I guess you could do, alright, so Vf squared equals V0 squared, which is 0, plus 2gd, okay? So that's your initial of the system, so I definitely got this wrong. So we can find the initial velocity is rad 2gd. So now we can use this with a mass of m for the brick. 2gd equals, now 1/2 of the mass is going to be at 0. So the other 1/2 of the mass has to be at some other arbitrary v. So if we solve for that v, this is 0. Okay, so we get 2 rad 2gd. That's rad 8gd. So that's the actual correct answer. It's important to read the questions correctly. It didn't actually say it hits the surface and breaks. If that was the case, it would be 0. So it wasn't. Alright. Simple harmonics not on it. I'll skip this. This is oscillation. Alright, cart's moving in the positive x direction. So velocity, Vx is greater than 0 at time t. Then the decreasing speed. So that means it's accelerating in the opposite direction of velocity. So ax is less than 0. All right, so we want to get the position graph in terms of time. Remember, this is the second derivative, less than 0, so it's concave down. But initially, the first derivative is greater than 0, so that's increasing. So it's increasing and concave down is what our graph should look like. Obviously, lines can't be concave down. Concave down, that's the answer. So realistically, for this question, it wouldn't actually matter what the initial speed or position is. You just have to get the concave down one with these options. All right, we have a force. The ball initially contacts the wall. Change of momentum. So change of momentum is F dt. All right. So we have a function, 300t. Just plugging in these variables, it gave us minus 3000 t squared dt. And our initial contact point at the collision, 0 seconds to 0.1 seconds. So if we integrate this, we get the integral of 150 t squared minus 1000 t cubed from 0.1 to 0. The 0 evaluates to 0, obviously. 100th, so 0.1 squared is in 100th times 150, 1.5 minus in 1,000th minus 1 equals 0.5. Now the units for this is Newton seconds, also kg meter per second. Set an answer, 0.5. At what time does the coin start slipping relative to the surface? Okay. Sure. Now, the definition of slipping here is, I'm assuming, it's when static friction is lost. So, F for static friction is less than or equal to mu s Fn. And Fn, that's from the reference table, Fn equals mg. Okay, because it's on a flat surface, it says. A rough horizontal surface. Alright, so let's set up this equation. Acceleration is bt. So F net is ma. So m times bt, which is a, equals I guess some force, right? Some force minus mu s mg. Yeah, I feel like so this is the maximum value of it. You can rewrite it as 0 to okay. M's cancel out. This is over m. So some random acceleration force. So at the time where this exceeds MSMG, I guess, I'm assuming it's mu s g equals bt. That's an answer. Why would that make sense? Essentially, this is saying that the maximum acceleration that the force of friction, static friction, will stay for is, if you like divide it by mass, is mu sg. So once acceleration exceeds mu sg, then there's no longer static friction. It starts slipping. So if at time, when the time is equal to this, mu sg over b, if you plug that into here, you get mu sgb, where b is a positive constant. So that will have exceeded it. I think that's the correct answer. I will double check that, I guess. Yeah, so my misunderstanding was that there's no real there's no real force here. It's just the surface is actually moving under the object. So you literally, like, the net force is like mbt equals force of friction, okay? But given that static friction, but you have to use this inequality from the reference table. So it's actually like less than or equal to this. This is like the net, whatever the net force. So it's from 0 to m u s f n, or m u s m g. So you're basically just finding the time that this inequality breaks, because once the inequality breaks, that means it's slipping. So once bt, either t is negative or bt is equal to mu sg. So yeah, so that's why it's t is equal to mu sg over b, because that's when the friction equality. Doesn't hold. Okay, let me see if there's any actual questions of value here. And I guess this probably got it wrong on the test. Straight up, this planet has no atmosphere, so saying air resistance is negligible. Very quickly reaches escape velocity. At that instant, the rocket's engine turns off. After a long time, the rocket moves farther away from the planet. What happens to the speed? I think it's saying that, like, the rocket initially has escape velocities. It initially does have no potential energy, but it does have an escape velocity. So like it's basically saying it instantaneously gets to escape velocity. So at a very long, far away place, we're asking what's happening to speed plus potential energy, or it's going to go to like 0. I think this is similar to like a test question. The potential energy. Okay. once the rocket's speed doesn't actually like theoretically never remains constant. Well, essentially, the escape velocity. What happens for escape velocity is when um, potential energy is equal to kinetic energy. So satellite. So what this means is like if the initial energy is whatever the escape velocity is, then by the time it gets out, it escapes the planet, it will have 0 energy left, I believe. Um, Hi Zach. To test this, I'm pretty much talking to myself, but I'm doing an escape velocity question. To test this, you can find that escape velocity is equal to 2 g mpr. So if you're given that the initial velocity and the radius is 0, 1/2 ms 2 g mpr. So this evaluates to g.
Yo, what's up, JT?
Why do you know that mechanical approaches 0? Well, mechanical is the combination of potential and kinetic. It's clear that like when you get really far away, potential becomes 0 because that's based on the distance. It's inversely
Yeah,
proportional.
that's
But the kinetic is there's work done on the kinetic by the potential. So like
what?
think of it this way, like even gravity is still exerting a force on the object, even it's not 0. It never reaches 0. But it's continuously decreasing as you get to infinity.
Wait, but why? Wait, if there is a velocity, it's escape velocity.
Initially, yeah, escape velocity. But then that's the minimum required. The escape velocity gives you the minimum required energy to get out. But then all that energy will be expended as you get infinitely far away.
So once it goes into orbit, it just stays there. Like it doesn't have a
Well, it
velocity.
keeps it keeps going further away. But eventually, if you went for like infinite time, its speed would get to 0, I believe.
Okay, so kinetic energy. Yeah, because I did this question when I was checking. ChatGPT said like, "Oh, you know that mechanical energy approaches 0." I'm like, how do we know that? But now,
Yeah.
okay, so that's why that makes sense.
You could like in terms of work, right? You could check this out. If you go from like the radius of the planet, like work is force times distance. The force is G MP ms over r squared, right? And dr, so that's time distance, and then we go to infinity. We can evaluate this, unfortunately. So this is negative G MP ms over r. I think this was supposed to be like, let me see. I think there's not supposed to be a negative sign, but you can evaluate this from rp to infinity. So at infinity, this goes to 0. Let me make sure I have this formula right. The force. Yeah, okay. So like that goes to 0. That's negated. So you get GMP. That's the energy expenditure from the radius to infinity. Um, but so like, does this make sense that the work done? So this is saying this is the force, right? The gravitational force, okay? And this is saying what is the energy loss? So the work done, or rather, the work done by gravity from the radius of the planet, like the escape radius, to infinity if it goes an infinite distance. And if we evaluate it, it gives us this. So this is saying that the work done as you go to an infinite distance is this, right? Does that make sense? Like,
Uh, sure.
well, look, this is
Not gonna
just
lie,
a,
I wasn't listening,
yeah,
so
that's
I
fine.
had to open
So
the
this is
door or
the
something.
force of gravity, and then work is force times distance. It's also the change in kinetic energy, right? So as we go from
Yeah,
the distance from the radius of the planet to infinity, if we evaluate that integral, the work done is this. So it's saying this is the change in energy, is GMP ms over RP, okay? So the
so
change.
that's how we get that formula in the reference
Well,
table. No?
that's how much the kinetic energy would decrease by as we go to infinity, okay? And we know that the initial kinetic energy is 1/2 mve squared, because that's what it says.
Oh, so
But
the change in work is like basically infinite to go
yeah,
to zero.
but if we want to find
Uh,
VE, okay, we've set the kinetic energy equal to ms mp over r. I think that's correct. I can never remember where the negative sign goes. Negative. Well, now it's positive. So,
wait, wouldn't it not matter?
well, VE equals 2 times 2.
By the way, JT, I heard you
Yeah,
have some competition in tutoring on video.
I have some what?
Some
Oh, Mr.
competition.
With my teacher?
Yeah.
I'm gonna go to that later. He'll probably give spoilers.
Oh yeah, that's true. I might have to do that too. And I gotta look over the FRQ because didn't he give like hints?
Something like
Swear
that.
he did
Yeah, we
that.
can look at.
He told us
So,
basically what
all
they
right.
were.
So we learned that earlier that the change in kinetic energy as we go from the escape, as we escape the atmosphere, the radius to infinity is this. Okay, RP, whatever. This is RP. And we also have this velocity, and we have the initial kinetic energy is 1/2 msve squared, okay? And we have no initial potential energy, or like our radius is, I actually have to think about that.
Wait, what'd you say?
Now, I was just thinking, um,
Initial kinetic energy?
yeah, this is our initial kinetic energy, okay?
Yeah.
And our initial, potential energy, actually,
It's just
maybe
wouldn't it
this
just be
doesn't,
gravitational potential?
yeah, maybe this doesn't work out. I don't think this setup is very good.
You
Equals,
don't need a setup, bro. This is
yeah.
conceptual.
Well, anyways, we would initially say we have 0 potential energy, I believe. Like, hmm,
Why
I don't
would
know. I was just thinking, anyways,
would you?
I don't know. I don't know. Anyways, so this is our change, right? If we evaluate this, it becomes G ms mp over r, though. So, like, if you plug in VE into this, you get this. But this is also equal to that's how much we also learned that the potential energy, the KE will decrease by. So KE will go to 0. Um,
Hmm.
Potential energy will also decrease.
Yeah.
Okay, yeah, it's just asking about the speed. Um, yeah, That's
That makes sense. I was just looking for the FRQ, the two units he
he
said
said
are
unit
unit
2 and
2 and
unit
unit
6.
6. Yeah. So what that could probably just be like resistive force and maybe like deriving inertia or something.
What is unit 2? Functions.
That could be like
I
resistive force.
suspect it's going to be a series and parallel spring thing.
Oh really?
So you should know about like the spring constants
Wait,
and stuff.
series is the one over and parallel is the
For
you
the
just add the spring constants.
So the properties of series is that they all have an equal force acting on each spring, and then 1 over ke equals like the what's it called? I forget what it's called. The equivalent
Spring
spring
constant?
constant, yeah, is equal to like 1 over k1 plus 1 over k2
Yeah,
plus
yeah.
1
And
over.
I mean that means it's easier to stretch, right? Like conceptually.
Oh, so conceptually speaking, it would
Oh,
have to be um
what did you mean
unit.
about the forces? Oh,
They all have an equal force exerted on them.
some of them it's what is it for the parallel?
1 sec. So let's say this has a like a so let's say there's two springs that each have a spring constant of k equals 2. So what does that mean for us? 1 over k equals 1 over 2 plus 1 over 2. So it's equal to 1. So k equals is 1. So yeah, it would be easier to stretch. It would have a smaller equivalent spring. What were we saying?
What you said the forces, so like okay, each spring
So let's say we have
it's
a right
the same
a
force.
spring, okay? And it's like they're connected, and then there's another spring, and then there's the block, right? Let's look at the like on each object. There's mg downwards, right?
Hmm.
But then this block has the block has a force of, so I'm gonna redraw the block mg downward. But then you agree there's a spring pulling it on upwards, right?
Are you drawing on the notes?
I'm drawing. Oh, you can't see it. You're right. Okay. So
I would say yeah. If it's just a block, I'd say there's tension probably upwards, no, in the
so
string.
you well force of the spring is upwards. So if we look at that
But
block.
if it's at rest, then it would be equal
Okay.
to
So
mg.
now let's look at that's bottom spring here. You agree that the block is pulling downwards on it, mg
Yeah,
downwards. But then
yeah.
the other spring is pulling upwards on it, fs2. Okay.
On the actual
on
string
on this
itself, yeah,
on this spring here, the top spring is pulling upwards on it, and the block is pulling downwards on it. So for
yeah.
that spring, we have mg downwards, fs2 upwards. Now for the spring on top, we have fs1 downwards, and then nothing's pulling on it upwards. Okay, like the ceiling doesn't really pull up on it, I believe. So we have fs1 downwards. That's the only force on this spring here. Okay.
Okay,
So
so
let's set up the
okay, but
fnet.
each of them contributes to F
Fnet
equally.
equals um mg minus fs1 because fs1 goes
You're,
upwards.
you're considering
But
upwards positive
so
or negative
minus this fs1, but fs1 also goes downwards, so plus fs1, and then we do,
minus FS2.
well, yeah. So what does this really show? Um, okay, so what is this showing us, right? Fnet, and we're gonna say this is equal to 0. So these fs1s cancel out, so we have mg minus fs2 equals 0, okay? So mg is equal to fs2, which is really interesting. So how do we know fs1? Because it cancels out. Well, we can figure out fs1 because on the if this has an fnet of 0, that means the system isn't accelerating, right? So that means this block isn't accelerating, so we can do a separate fnet for that. So for the block ma, a is 0 equals mg minus fs1. So that means fs1 equals mg. So they're both equal
Right.
to mg. So
Uh-huh.
fs1 equals fs2.
Okay. That makes sense.
For parallel, you can clearly see that they might have different spring constants, but their displacement's gonna be the same because we're assuming the springs are not gonna we're assuming the platform's gonna stay flat. So that tells us that the spring constants add on. So let's say we k equals, if we wanted to replace this with a spring, one has a spring constant of 2. That's like Newton. I think it's like Newton per meter or something. The other has
Wait.
a spring.
So if the k values of the series are different, then the displacements are different.
Sorry. Yes. Well, yeah.
Like
For
it
each
makes up for the
individual.
fact that the
For
forces are the
each
same.
individual.
Okay,
Yeah. Like if the K value of 1 decreased, its displacement would have to increase.
does it matter like which one is directly holding the block, or like that doesn't
Mm-mm.
matter?
Mm-mm. No.
Okay.
So for this, they all have the same displacement. So the K's add on. You can think of this conceptually. If we wanted to replace these two with another one that would have an equivalent spring constant, that means that its displacement would be the same. It would have to be a stronger one, a sturdier one, so it would have a higher K.
But it would still displace the
If you
same.
wanted to have
It would just take more
it
force.
would have the same displacement. It would take more force, so it would have to have a higher K instead of having two
Okay,
different springs.
got you.
So recap. So I think it will be a spring thing. Or actually,
I don't know. I disagree. Yeah, I think it would be drag force
but
or
there's not
resistance.
much to do with it unless he like slightly changes it.
The spring, there's nothing to do though. Like drag force, he could be like, okay, derive this, which
It
he's
could be.
given us like 10 times, but he could still do it.
You think he's really gonna ask like? So we have A equals
I
what is
think
it?
he will. I don't
G.
see he did it. He did it on. Remember, he did a handout
Yeah.
worksheet, and one of them was like just that basically.
So we have well, it might say the initial velocity is different. So from 0 to
Yeah.
v of what is this? That's dv over dt is A.
Hmm.
1 over g. I'm gonna do this with u sub because it's quickest. dv equals
It's too
integrals
difficult.
dt. So that's gonna be equal to t. And this is I'm gonna let u. So that's I'm gonna u equals g minus bv over m. So v. So
LM.
du equals negative b over m dv. So we have a dv
Oh,
here. We can substitute negative m over b du equals dv. So we're gonna replace this dv with that. Um, so what I can do negative m over b from and since we have a u sub, this is actually saying u of v. U is actually a function of v. U is a function of v. So we have to transform the bounds. So if we plug in 0 for v, we get g minus b times 0 over m. So
G.
that's g. Now if we plug in v for v, we get exactly that. G
Yeah, G
minus
might be on.
bv over
Sure.
m. Okay, now we have this, and it's 1 over u du equals, we have t. I'm gonna now for simplicity, I'm gonna rewrite this g minus bv for m 1 over u du equals negative b over mt. Okay.
Tough.
Now integrating that gives you absolute value ln of u evaluated
Plug in.
from g minus bv.
Oh, you plug in after, or you
Yeah,
don't have to.
we'll plug in after. 'Cause negative So now let's plug that in, absolute value. So I'm gonna use the log rule, so it's division. I'm gonna just skip some steps, do that really quickly. G minus BV over M
Over G.
over G, because it's subtraction.
Type.
Now if we simplify, well, let's raise everything to the E, okay?
Yeah.
So we get 1 minus BV over MG equals e to the negative b over mt. Now we have to do something else. Let's say theoretically, right? If we were to go on for an infinite time and there was no like ground, never hit, eventually the drag force, because velocity would keep increasing, drag force, which is bv, would eventually equal the force of gravity. Net force would be 0, meaning there's no acceleration, the velocity is constant. So that's when we reach terminal velocity. So that's a theoretical thing. Um, so if we were to do that, that's when BV equals mg. So we would find V infinity. I'm gonna write instead of V terminal. That's after infinite time. Would be mg over V. So we have a 1 over V terminal equals B over mg. That's actually present here. So we can do, if we do some substitution, right? We can do 1 minus, wrong. 1 minus, what is it? V over V terminal equals E minus B over MT. If you gave us like a different starting time or something, it would be really annoying. So we multiply everything by V terminal. So we get v terminal minus v equals v terminal e to negative b over mt.
Why do you use infinity as a subscript?
Instead terminal vt. It doesn't
I know,
really
I'm just
matter
used to it because on
because
the
well
notes it was VT.
I don't do vt because it looks really similar to v of t, which is a function, and vt is a constant.
Oh,
That's why I don't like it. So if we actually rewrite this, negate both sides, negate it, right? We get I'll write, see, now I'm gonna write it as v of t because that's a function of time, minus v terminal equals negative v terminal e to negative t. Okay, now what we do is we move that v terminal of v of t equals v
see,
terminal of 1 minus e to negative b over mt.
you just proved it right.
Yeah. So I like this because if you just like look at this as some arbitrary constant, if you ignore all this, right? We know what like e to the x looks like. Now, if we were to negate the x, like that's the same as flipping it around the y-axis, e to negative x, okay? And then
Yeah. Oh, and then if it
if we do
approaches
that
approaches one
if we negate it again,
over
it's
infinity.
going to look like that, but flipped over this way. And originally, e to the x has what asymptotes? It has here, right? And there's actually no
Wait.
vertical
Oh,
asymptote.
so that e function approaches zero, so it just approaches one minus zero, which is v
Yep,
terminal.
yep. So the
That's
asymptote
actually
goes,
tough, bro. Yo, physics is hard.
cutting out a lot, but yeah, I get what you're saying. Um, so yeah, as this goes to infinity, 1 over e to the whatever goes to 0. So that becomes 1 times v terminal, which is a nice v terminal. Do you want to do the other way besides u sub? Should I do that?
Nah, I think I not no because when we were first learning it, we didn't really do U sub like in calc yet. But now I think I get U sub better.
He's not gonna give bv squared because I did it yesterday. The integral, when you
Do it.
when you do bv squared, it doesn't work out really nice at all, I think. Wait, let's see.
Yeah, he. I mean, he's gonna be fair about it. Like,
Well, then he has to give the exact same thing pretty much. So look, this is bv squared. I'm not gonna make you read through it. I'll just show you the final answer. Um,
bro, that's too much work, bro.
v
I would
ter
ju-
v
honestly,
v
I'm
terminal
taking partial credit if that
v
comes up.
terminal, I'm sorry, v of t equals v terminal over g times hyperbolic tan of g squared over v terminal times
It's
2.
hyperbolic tan.
It's like tan, but for an ellipse instead of a circle.
That's doing it.
Yeah, I agree. So
There's absolutely he can't ask that because no one knows what that is except maybe like you and some smart people.
I I don't think anyone knows the hyperbolic tan identity. So
Maybe like Lippmann probably.
I don't
Ben.
think you would know it. Like it's just a thing you memorize because you're not gonna
Dave might know it. Micah.
maybe.
They might not just know it from doing math.
Yeah, that's true. So it could be that. He could actually ask us to do acceleration. So what if? So let's say he
And
has
then
for
you just
excel.
take the you take the integral, no?
Let's find position and acceleration actually. So
Bro, that's too much. That's just calculus.
yeah, well, let's do it because it could be asked. So the integral of v of t to find x of t.
Bro, that's
So
just annoying calculus.
oh, I agree, but I'm just gonna do it real quickly. Uh, equals. So I'm gonna write this out. Minus. Yeah. So if we do that, x of t is gonna be equal to some x initial xi plus terminal velocity times time. Um, and then this is gonna be plus
But
terminal.
why are you doing it in your head?
I don't know. Divide by
Don't you
b over
need
v,
like
and
don't you need to do what's it called? Oh no, it's a constant. Never mind. You don't need to do that. That's not that bad. That's actually not that bad.
yeah, that's x of t. So
I
there's some
forgot v
so
terminal was a
it could say
constant. No,
give me.
that's not.
He could ask you to find the position at some time, but you would have to know the initial position, or it could say find the change in position, in which case you don't need that. Let's say it asks for acceleration, right? We're gonna use this same That's actually v of t here. X of t equals. So we're going to use v of t and we're going to differentiate it. So a of t equals the cancels out. Then you multiply. So equals negative this times negative b over m t.
Mhm.
Yeah, I'm sorry. Times then
No,
e
is
to
that
negative
right?
b over mt. So um, you could
Wait,
actually like
hold up. Did you do distance right?
yeah,
Why m over b?
because you divide by this. Dividing by
It's
b
a
over m is the
derivative.
same as multiplying by m over b. No, distance is
Yeah,
the
what?
antiderivative because we start with velocity.
Oh wait, yeah. Hold
Yeah.
up.
So we have this is true. So mg over, so we can rewrite this equals mg over b times b over m e to the negative b over mt. Let's actually do that. If we cancel these out,
Wait, that's actually nice.
g e to the negative b over mt.
That's actually looks nicer than the other one.
Yeah, because like, so acceleration initially at 0, that becomes 0, right? Oh, that becomes 1. This term evaluates to 1 at 0. So the initial acceleration is gravity, right? And as we know, when you get to terminal velocity, acceleration is
There's no
0, right?
acceleration.
So if we plug in
Oh, so when
infinity,
t goes e to the negative t or whatever goes to 0. Yeah, that's tough.
yeah,
It's like it's not easy like when you see it, but I feel like when you're locked in on the test, this is not that bad.
yeah. Also, what was the other one? He said unit 6, right?
Oh,
What's
unit 6 is gonna probably be like moment of inertia derivation,
uh
probably.
important? Yeah,
That's my guess. I mean,
could be
it makes
Kepler's law.
sense as long as he doesn't give like a really annoying one. Oh, Kepler's law. I don't know those.
It's
I
just
know it's
saying
like I know like the conception is like the area or something
angular
is equal in
momentums.
each like period, like fraction of a period. I don't know.
Yeah, it's just saying angular momentums conserve. That's all you have to know. You don't have to. You wouldn't have to like do.
Oh, in like an elliptical angular momentum's conserved.
Yeah,
What about first law? Do you have to know that?
I don't know what the hell that is.
I remember. I know. I don't think we did. We learn that? Isn't that something like gravity?
Let's
Like
see.
when in the inner shell stuff with like the I don't know what it's called when it goes like
There's. It
inward
just says
radius.
there's two foci.
Oh, is that different?
It's not relevant for us.
No, not this one. I was thinking. I thought his law. He had a law about, or someone had a
Newton.
law.
That was Newton. I did
Oh
a
shit.
question on that before you joined because you
The
asked
one,
me
the one
to.
that I told you. Yeah.
Yeah, so you can watch it back. It's like the first minute.
Was it? Did you think it was tricky, or was I being stupid?
So question. I'll just go back to it. So this one that you sent me. Oh, that's not the. This
That's
one.
the answer.
Uh, I believe
Wait,
so.
to hold up.
I explained because with friction, right, if there's rolling, energy is conserved because it's asking about the energy of the sphere ramp Earth system, so that's literally every object. But it's asking about total mechanical energy, so that's only potential and kinetic, right? So let's say there's no friction, it's obvious that energy is going to be conserved because what you lose in potential you gain in kinetic, right? But let's say there is like complete like high friction, right? So it will roll and it won't slip. So what that means is it's going to lose some energy as friction, like the force of friction, right? We'll do some work on it on the sphere. Does that make sense?
No.
So listen, when the friction's really high, as it rolls down, there's static friction, right?
If the friction's high and it rolls down, there's static friction. Yeah, I
So
guess so.
so the force of friction is going to do work on the sphere, right? Because it slows it down.
Yeah.
But that same, because of Newton's third law, each force has an equal and opposite reaction. The force of friction will also do work in the opposite direction on the Earth. So the
Oh.
system will keep the same amount of energy when friction's really high.
Isn't like is this the formula like work due to friction is delta me or something?
It doesn't matter. It's not delta me.
I know. What I don't know. What
Let
was
me
that
change.
formula? I don't
It
know.
depends. Okay, anyways, just listen. So any energy that the sphere loses due to friction, the Earth gains. So the total system between the sphere, Earth, and the ramp is going to have the same amount of energy for really high friction. But let's say friction somewhere in between. That could mean the sphere is sometimes slipping, right? It's sometimes slipping, but there's also friction. So slipping will cause it to actually. I had to chat GPT this because I thought it was B, but it's not because if they're slipping, some mechanical energy will be lost as heat energy. That's why this question is kind of stupid. Slipping can cause friction to make heat. So,
But it never said it was slipping.
well, but that's implied that there's a low enough friction value that it can slip.
It doesn't.
That's how all
Oh,
objects work. If the coefficient of friction is too low, the object will slip.
I don't get why that is.
Um, because you can think.
But not zero. If it's no friction, it doesn't slip. Or
So slipping, right? So slipping is when there's no static friction, right? And
mm,
static friction, there's an equation in the reference table. Fs is less than or equal to
yeah, yeah, yeah. Mu
us
Fn.
mg or whatever. Well, Fn, which depends. So that means that if the force acting on the object is too high, there won't be static friction. So that's when it's slipping.
Mhm. Okay.
So so um you can think like, but there could still be a force acting on it. So like friction could be anything between 0 and mu SFN. So let's think of it this way. If there's a little bit of force of gravity acting on the object, it could be perfectly like opposed by friction. But there's a certain threshold it reaches in which it breaks out of friction, and that's when it starts slipping. But because it's not but because there is friction, like still, or there was friction, that means that it caused it to have some speed to some extent. So like it may have some speed. Um, this graph is not a perfect representation of how it would be, but like you just have to understand it reaches a certain threshold in which it loses friction.
Okay. And then once it reaches it, it comes back. Where the energy is just where it started.
Yeah, at first if there's no friction, it's not going to lose energy to friction, right? Because it's the ball's literally going to go down, it just won't roll at all.
So
Like you can
basically, once the mu constant is like way higher, it has to be like a small one for it to be in that range. That's why the graph looks like that. Okay.
yeah.
But not zero. Small, but not zero. Okay. Somewhere in between those. Okay. Fair enough.
Um the other
Kind of like.
one The other one I explained before, but it's fine. The mass enclosed is equal to the density of no matter what sphere, any portion of the object you cut out of it will always have the same density. That's what we're assuming. So if we find the mass enclosed, right? Newton's shell theorem says that the force of gravity will be based on the mass enclosed by the object. So like that's G m the m stone times the mass enclosed. Okay, over the distance is d squared here. I did this earlier, but the mass enclosed is equal to the density times the volume enclosed. So that's pi times d cubed. Okay, so that's the m enclosed as the density of the object times the volume enclosed. So the density of the object is mass of the planet over 4/3 pi rp cubed because the density stays constant. So if you simplify all this by plugging that into here, like you plug this into there, this is the answer you'll get is B.
But you could probably just notice that it's inside of the planet and
Well,
say like,
actually,
okay,
no.
the rest of these can't
The
be it.
shortcut you would take for this question is that RP is always a constant. There's only one changing value is D, right? D is the changing value. But what we learned, the Shell theorem states that while the I guess the radius enclosed, or like the distance from the center mass of the point mass, is within the planet's radius, it will increase directly proportional. So you'd have to choose the option that has a directly proportional answer. So D is what it's a function of. Gravity is a function of D here. So it would have to mean it would be multiplied by D, like it would be linear.
Oh, okay, and B's okay. B's the only linear. Fair
Yeah,
enough.
yeah. Do you
I
want
would
to
I
do?
would probably like I picked B because I saw it looked like something that somewhat resembled those questions we've seen in the past. But I don't know. Okay, this one
Is this good?
I
Should I
think
do it?
ChatGPT got it wrong for me because this one seemed obvious
Okay.
when I was checking,
But
and it was like,
we
nope.
have to do it. So all those three torques in the middle, they don't cause, or all those three forces don't cause any torque. Um,
What?
Oh, it's just those are the radii. My bad.
Oh yeah, those
Okay.
are radio. I was gonna say.
Okay,
That's
counterclockwise is
okay.
positive. So we have three. So torque net is equal to T net, right? Equals I alpha
Yep,
equals
yep, yep.
three
R
F's
sine theta plus R sine theta plus R sine theta
plus RF0 minus.
minus. Okay, I got it right then. I don't know why ChatGPT was kept
What did
adding
it
that
say?
to
And what did you
RF
use over IS? Yeah, you divided by I.
over alpha over I. Yeah,
That's the answer.
exactly. But chat for some reason ChatGPT kept saying no. You add the one with the radius of 2. I'm like, no, you don't. That's clockwise.
All right.
So I don't know.
Do you want to do anything
What else?
else, or are we done?
I have to leave in like a minute.
Yeah,
But
I'm gonna study Spanish vocabulary, and then I'm
ready for BC tomorrow?
um BC. I study 20 minutes. I'm not wasting time on BC.
Bro, you're too cracked.